Okay, so example 4, 5, and 5 need to be a lot more creative and algebraic review. Example 6 is pretty straightforward. Now, as a little cheat sheet, if you scroll down, I'm going to go through this though. If you scroll down, I have these typed up though. For example 4, I have the explanation. See how long that is? And for example 5, whoo, these are long. But they're there. So I'm going to try to squeeze it in, but you just saw how long these are. These would typically not be on the Calc 1 AP exam. This could be on Calc 2, but you saw how long this is going to take, okay? There is a shortcut though at the end. I just can't tell you what that is yet. All right, so what happens is you have, if I did infinity, so I have e to the infinity plus infinity all over 1 to the infinity. And so this becomes to the 0 power. And so if we go back up here and we look, see, infinity to the 0 power is indeterminate. So both of these, example 4 and 5, are kind of in the same. And this should stand out because it's a limit and it's to this weird exponent, and we never saw these in our limits unit. So if you saw this on an AP exam, you would be like, wait, that looks really complicated. Oh, I bet it's L'Hopital's rule. And you would be right. But I don't even think these are going to show up because of the time. It's just not worth it, honestly. But if we wanted to do it, what ends up happening is I have to define a new function because we have an exponential. So the idea is we can get exponentials down if we use logarithms. And since we have e, we're going to try natural log. So what happens is we just let some new function, I'm going to let it be z, equal this. Okay. And then we can, as long as we take the log of both sides, we can do this because it's fair. So I'm going to take the natural log of z, and we can't take, z can't be negative, so we're going to make this absolute value. And then natural log of this. As a review from Sec 3, if you had natural logarithms, there was a power rule. And what that did was that took any power and it brought it right down in front of the log. So we need to do that. We want to do that, I'm sorry. Okay. And so really what ends up happening is we've got, because this was our z function, we let that be z, I really have the limit as x approaches infinity of, we changed it though, and it equals this. Now these I can write as one fraction. Okay. All right, so we're gonna do, if I evaluated infinity, well, I'd have the natural log of infinity plus infinity, which is still infinity, all over infinity. So it's indeterminate. So I get, we can ignore this for a second, the limit as x approaches infinity, and then we're going to do L'Hopital's rule. So in our numerator, we get 1 over the inside times the derivative of the inside. So e to the x and 1. The derivative of x is just 1. And so I can really write this as the limit as x approaches infinity of this over this. And then we want to try to evaluate that with L'Hopital's again. So if I plug in infinity, I'd have infinity over infinity, and so that's also indeterminate. So I need to do L'Hopital's rule for the second time. We get the limit as x approaches infinity. Sorry, I'll change my colors back. The derivative of the numerator. Oops. This needs to be an x, I'm sorry. over the denominator. And so then we evaluate again. I had infinity over infinity. So we need to do L'Hopital's rule again. So this will be the third time. Okay. So we get the limit as x approaches infinity of e to the x stays, and this is just e to the x. Well, e to the x over e to the x, this is 1. So the limit as x approaches infinity of 1 is 1. Okay, now this is not our answer though, okay? So remember though, what we found was this limit. So now we need to set this natural log of z, because that's what we said z was. So z is this function. So the last step is that we know our limit of the original problem, okay? That's going to be, I'm gonna write it down here. So equals, our original function is equal to the natural log of z, which natural log of z means it's based e. So it's going to be e to our power, because that's what we found as our limit. Okay, now, will it always work that way? Yes. So if you had to rewrite using logarithms, and that's the way you're going to do it on number 5, whatever value you get, because you use natural logs in the original substitution, that is going to be your exponent for e. Okay, natural log is base e. And that's what you found. All right. The longer explanation, that's my shortcut. The longer explanation is down here. So we know this is our original function. Our limit as x approaches infinity of z is the same as e to the z, because e and natural log cancel out. So we haven't changed anything there. And then remember, z was our limit of the natural log of z. So that's why whatever we found for this ends up being the exponent. Okay? All right. So we're going to do the same idea on number 5. If we plug in 0, well, the cosine of 0 is 2 times 0 is 1. So the cosine of 1, remember, this is in radians. So we have 1 to the 1 over something really, really, really small is going to be large. So this is 1 to the infinity, which is indeterminate. Okay, so we're going to do the same idea here. We would let this equal z. Take the natural log of both sides. That natural log is going to bring the power down in front. And then I can evaluate my limit. It is the absolute value too. I don't worry about my absolute value, but technically it is still there. So what do we get? I can make that in my numerator all over this. So now if I plug in 0, so it's the cosine of 0, which is 1, and I could take the natural log of 1. So natural log of 1 says e to what power gives you 1? Well, that's 0. Then if I plug in 0 squared, I get 0. So this is 0 over 0, which means it is indeterminate. So we need to do L'Hopital's rule. So the limit as y approaches 0 from above, we get 1 over the inside times the derivative of the inside, which is kind of a chain rule. The derivative of cosine is negative sine. Its inside stays the same. And then we have to go back and do the derivative of the inside. Y squared is 2y. So if we plug in 0, well, the sine of 0 is 0. So 0 over, as long as it's not 0, that would be 1 times 2. So this would be 0 altogether on top. plug in 0 here, and I get 0. So indeterminate, we're going to do L'Hopital's rule again. Limit y approaches 0 from above. This one I would actually make, so I don't have to do a quotient rule, we would have 2, -2. Sine over cosine is tangent. The 2y, I can combine them because the insides are the same. All over, this is going to stay 2y. I haven't done L'Hopital's rule. So now I'm going to do L'Hopital's rule. I just wanted to change that because I don't want to do a quotient rule derivative if I don't have to. So we get the limit as y approaches 0. So I get -2. The derivative of tangent is secant squared 2y times the derivative of its inside is 2. The derivative of 2y is 2. And so now it should end up that this is not indeterminate because we have a 2 on the bottom. I would rewrite this so we get -4 over secant is cosine squared. This is all over 2. So now if we plug in 0, I'm not undefined because we get the cosine of 0 is 1. 1 squared is 1, so I get -4 over 2, which is -2. And that's my limit. So remember, though, I still had like natural log, it's the limit of e and all that other stuff. So this ends up being e to the -2. All right, and I'll show you all the way down here the formal notation. I'm just lazy, so don't write it out. Remember, that's our original function is equal to the limit of z. We can rewrite that as e to the natural log of z because e and natural log cancel out. And then we just did the natural log of z. And so that's our exponent, which is -2. All right. Now, remember this special trig limit, the limit as x approaches 0 of sine of x over x. So if I plug in 0, I get 0 over 0, which is indeterminate. But remember, we used that idea of if we had a sine wave, and we had y equals x, and we zoomed in and we looked at their ratio, they were the same. So this ended up being 1, and you were supposed to memorize that. Well, what if we don't memorize that? Since it's indeterminate, can't we, because it's 0 over 0, when we substitute 0, can't we use L'Hopital's rule? The answer is yes. So if we use L'Hopital's rule, and not our memorized rule, incorporating the ratios, because this was before we knew derivatives, the derivative of sine is cosine. The derivative of x is 1. And now if we try substitution, we get cosine of 0, which is equal to 1. So it works with the ratio idea because that's the underlying principle of evaluating limits. And it works with L'Hopital's rule because it's indeterminate. All right, so there you go. I give you quite a few to practice. I think it's on a separate sheet though, because this one was a really long sheet. I let you pick problems. Go ahead and pick the ones you want. They really don't get super complicated. I have the answers and I have worked out solutions if you scroll down further. All right. So email me if you have any questions.